So what's up guys, this is me again, your resident chemistry tutor Mark, and for this video, I will be discussing electromagnetic induction. So this is the first part of the many-part series of EM induction. So for this video, we will be discussing how Faraday discovered this phenomenon that was heavily credited to him and which I believe made him rose to scientific fame. And then we will be probing with the physics of EM induction, and finally we'll be discussing about Lenz's law. Okay, so we'll start. So who is this guy who discovered electromagnetic induction? So Michael Faraday is during his time he was really well respected in the scientific community, mainly because he made significant discoveries not only in electromagnetic induction but also in physics in general and chemistry. So in chemistry, he was heavily credited for his work on electrolysis and electrochemistry in general. So if you're familiar sa electrochemistry, ang Faraday's law, ang kay Faraday nga, what do you call this, ang EMF, he was heavily credited for that. And also he also discovered benzene and the class rate hydrates of chlorine in the field of chemistry. Now, so how did he discover electromagnetic induction? So actually, this is an illustration. What we've shown here is an illustration of his original experiment. So in his original experiment, ang purpose niya lang sa ining experiment is to determine the magnetic field created by the iron ring. So he has an iron ring here, and this iron ring is wrapped with two individual coils of wires. One is connected to a complete circuit with a switch that can open or close the circuit, and the other is connected to a galvanometer. So this one, the galvanometer, or in our term, it's what we call the voltmeter. So that one records how much voltage is recorded in the instrument, is received by this coil of wire. So ang purpose lang at first is when he switches on this circuit, so there will be a current flowing through this coil of wire, okay, through the left side coil of wire. Now, to the left side coil of wire. Now, a purpose niya lang is if this coil of wire induces a magnetic field on the iron ring. Well, he discovered that it did induce a magnetic field on the iron ring. Apart from that, he also discovered that when there is a magnetic field here, there is actually an abrupt recording on the galvanometer on the other side of the coil. Remember that this coil, these two separate pieces of coiled wire that does not have direct contact with each other. So their only connection is the soft iron ring. So thus, they do not. This one cannot conduct electricity. This one, which has current flowing through it, cannot transfer current into the other side of the ring. So that puzzles him. Nga may recording sa galvanometer, even though it is not in contact with the closed circuit here when it's switched on. And also, one thing he noted is that when he switches on, the recording of the galvanometer is abrupt. It's just abrupt. After that, it will revert back to zero. Ang muna na-discover niya. So, he was really curious what was happening, and he repeated that on other experiments. So he repeated this in an open or closed switch, and when he repeated this using using two coils of wire that are just adjacent with each other. So wala contact. There is no iron ring, maybe, that can conduct the electricity from one coil of wire to the other. So space na gidjanga separate sila, or basically air. So when he opened or closes the switch of the wire that is connected to the circuit that is connected to one coil of wire, this other coil of wire, which is not connected to any circuit whatsoever, gives an abrupt record on, I think this is an ammeter, or the one that an instrument that records current in a circuit. So this coil is not connected to anything. It's only connected to an ammeter. So in open close ang switch, he noticed that when he opens the switch, there is again an abrupt reading, and then back to zero siya. Pero when he turns off the switch, so that means he breaks the circuit, there is again another reading on the opposite side. Again, a reading on the opposite side, which is also observed, by the way, which is also observed in his original induction ring experiment. Kung i-open close naman yung switch, naga-oscillate man ang recording sang imo galvanometer. It goes like this. If you can see, I don't know if you can see. Yeah, it goes like this. Now, when you do that to two adjacent coils, which is not connected to anything, so maybe gintisingan niya in order to rule out the possible interference of the iron ring, because iron ring also conducted a current, pero if it's a conductor of an electricity, that means the recording of the galvanometer should be consistent. So it should not be abrupt, then makato siya sa zero once the circuit on the left side of the induction, on this side of the iron ring, is kept closed, the circuit here. So continuous ang flow ng current, dapat continuous man di ang reading sa galvanometer, but that is not the case. Abrupt, then back to zero. Pero when in this case here, wherein the two coils are separated by only space, by air, so when he opens the switch, abrupt man, pero zero. When he closes the switch, abrupt, zero. When he opens it, abrupt on the opposite side, zero. So kung i-open close mo ang switch, the dial of the reading instrument oscillates back and forth. Now he tried this with a magnet, and when he pushes a magnet downward, when he pushes the magnet into the coil, the magnet oscillates to the left, and when he moves it up to the coil, the magnet oscillates to the right. Okay? So, pero when after moving the magnet downward or upward, the magnet was not moved, it will revert back to zero. So again, abrupt man Japon ang reading. But when he pushes, or when he does an oscillating motion of the magnet, of the bar magnet here, the reading will also oscillate here. The same goes with the horseshoe magnet, wherein ang coil naman ang ginapamove mo. So gamove man ang reading sang imo nga instrument. So that is from those observations, he postulated that the change in the oscillations in the magnetic field also induced a current on the coil. Thus, the electromagnetic Thus, electromagnetic induction is born. And now we will proceed to the physics behind electromagnetic induction, okay? So, don't go away, stay tuned, I'll be right back. As we have discussed in the Faraday's discovery of electromagnetic induction, he repeated the experiments into several into different setups. He repeated it so many times, and he observed the same result. There is a voltage, or subsequently a current can be induced into a wire when there is a change in the magnetic field passing through that coil of wire. And since we have already discussed magnetic flux, we will introduce the law discovered by law conceived by Faraday's experiments into the terms of magnetic flux. Now, this law is what we call the Faraday's law of electromagnetic induction. Now, as stated by Faraday's experiments, a voltage can be induced into a current, into a conductor, or into a coil when there is a change in flux. Along the change in flux in the area that is in the area of the conductor as time passes. So basically, the induced voltage, which is denoted by this expression, is equal to the change in flux over time. So this is delta T. So because or sometimes T na lang kay it is assumed that ang initial flux, ang initial magnetic flux passing through a coil of wire is equal to 0. So ang final time at time t, so the t minus 0 is equal to t, right? Now if the wire, or if the coil, it consists of n loops, therefore this Faraday's law of electromagnetic induction is modified such that we incorporate the number of loops in our equation. It will look something like that. Now, since flux is equals to the magnetic field passing through an area perpendicular to it, therefore, our induced voltage is equals to N delta. Remember that we have to enclose this in the parentheses to indicate that there can be both a change of the magnetic field strength and or a change of effective area or area perpendicular to the magnetic field in order to induce a change in our magnetic flux. So if you remember Faraday's experiments earlier, I'll just show it here. Wait lang. Oh, right. I turned it off. Sorry. Okay. Oops. Now, if you can see in his experiments, when you open or close the switch here, there is a current here. Now remember that your current also produces a magnetic field. Direction is indicated by the right-hand rule of field, so there is a magnetic field here. I'll just not indicate which is their direction. Okay? So from zero magnetic field, you have a magnetic field passing through this coil of wire here, which records since there from 0 to a presence of a magnetic field there, that means there is a change in now the magnetic flux experienced by the coil of wire here. So amo na nga may induced voltage. Same goes in this case. Since you push and pull the magnet, remember that the magnetic field strength changes with the distance between the source of your magnetic field. Okay, wait lang. Between the source of your magnetic field. So, when you push the magnet down into the coil, the magnetic field increases. The magnetic field strength experienced by the coil increases, which in turn will increase its magnetic flux. When you pull away the coil, or when you pull the magnet away from the coil, its magnetic field strength decreases, which also in turn decreases the flux. That is why there is a change in the voltage. There is a change in the reading of your either galvanometer or an ammeter. Thus, there is a production of an induced voltage or current. Same goes with the third example. So, going back to our discussion. That's it. So, muli siya, di ba? Let's try looking at let's try scrutinizing it by giving a simple example here. Oops. Okay, where is it? Now, let's say we have a magnetic, we have a conducting rail here. Let's say this is U-shaped. We have a conducting rail here, and on top of the conducting rail is, let's say this is a wire, or a thin wire, a thin wire made up of a conductor, and the rail has, I can say this is a length, a width, which is what we call L. Which is what we call L. So this, at the distance L, this is the ends wherein the conductor, the wire is also in contact with the conducting rail. And now, the length, the conducting rail is at a distance W1 away from the edge of this side of the rail. Okay. Now we move it at a velocity valuing of v. Then after some time, its distance from W1 will increase to W2, right? And also, we don't forget that there is also a magnetic field present here going into the page of this board here. Remember ang atong nga denotation sa magnetic field. So when it is dots, that is going in. When it is X, this is going out. So pagwa siya, paamo na. If it's X, this is going in. So it goes through the page of the paper, or in this case, whiteboard. So it will increase at a distance t. Now, at a distance W2. Now remember that this one is an area, right? Since the area for this one is equals to LW1, which is ang area sang square, or an area of a rectangle. The same goes here. Since the L will, let's say, what do you call this? Let's say you moved the conducting rail perfectly, such that it did not skew at an angle. So this one is exactly perpendicular to. This one is exactly parallel to length L of the rail. When you pull it after, it's still parallel to the length L of the rail. Thus, the area covered here will be LW2, right? And remember, in our Faraday's law of electromagnetic induction, on Faraday's law in electromagnetic induction, the induced voltage is equals to the change of flux over change of time. Now, in this case, the change of time will be simply to t, because we assumed that before we pull the rail at a velocity v, the start time will be 0. So ang theta will be equal to t. Ang delta theta will be equal to ang time after nga ginpull mo siya. Okay? So, and remember that the change in flux is equals also to the change of area or the magnetic field strength, either which. Okay? Now, since the magnetic field remained constant, therefore, the magnetic flux, the change in magnetic flux is equals to, we take out a magnetic field since this is constant, so B sub null delta A. And remember that the change in area is when the distance of the conducting rail from W1 changed to W2. Okay, so area is A2 minus A1. Therefore, substituting the expression for area that we have obtained earlier, it would look like this. Is equals to W1. Sorry guys, may nagsulod sa office. So, anyway. Therefore, okay, I'll take out another board. Therefore, our induced voltage is equals to B delta A over T, or B LW2 minus LW1 over T, or we factor out L is equals to BL W2 minus W1 over T. Okay, I hope you can see. Okay, so now let's try to scrutinize how the presence of an electromagnetic, how a change in the magnetic flux, or the magnetic flux induced a voltage and consequently a current into our conductor and so in our conducting rail. So, diba? Wait lang. God, it's so hard to navigate. Okay. So sorry guys. So remember that we have this kind of equation, this picture here. Okay, we try to zoom it in. What is really happening, particularly on the part only of the conducting rails. Okay, so let's zoom in on our conducting rail. Sorry. So we have a conducting rail here. Not on the conducting rail, on the wire, or on straight nga conductor. So this is, let's say this is our conducting rail, and this is our wire, or our conductor, the conducting material. Now, so remember, as a conductor, I'll try to relate this in the perspective of chemistry. As a conductor, conductors have vacant orbitals, right? Particularly metal conductors. So they have vacant valence orbitals, or empty orbitals, and in the physics sense, they usually denote that. They usually call that as charge carriers, or particularly as holes. So basically, a hole is just a deficiency of a magnetic charge, of an electron. So we have holes here. So what happens is when you move the wire at a certain velocity, the charge carriers, or the holes, or the vacant valence orbitals of the conducting material will also move, will also experience a magnetic force going up. This is remember that we have a magnetic field here. So in the presence of the magnetic field, when the conductor is pulled to the right at a velocity v, it experiences a magnetic force upward, which is Fm. Okay. The direction of the magnetic force is as predicted by the right-hand rules of fields. Wait lang, guys. Wait lang, okay? I'm fumbling. Now, when we move it, what happens next is, di ba laging move na siya? What happens next is the holes will also move. Let's say the holes will move upward, and since there is a deposit of positive charge here on the upper side, what will happen there is, since the holes will move, since the vacant orbitals, it's not actually, this is hard. This is really hard for me because they actually perceive a current as a movement of positive charges. They actually perceive that the vacant orbitals, or what we call holes, also move, just like our electrons. However, we know in chemistry that only the electrons move, but not the vacant orbitals. So what happens here, since this moves here on the opposite side, that means, as a consequence, your negative charges will deposit here on the opposite side, in order to balance the charge, the overall charge of the conductor rail. Okay. Now, since there is already a separation of charges here, that means there will be an electric field present in the gap between this reservoir of positive charges or holes and this reservoir of electrons. Now, let's try looking at. Now this will continue. Now they will continue. As you move the conductor away at a certain velocity, the greater the separation of the charges will be. Now let's say their separation is not yet complete. I have not another. Wait. Let's say that the separation of their charges are not yet complete. So let's try. Wait lang. Alright, so let's try zooming in here on a single positive charge, a single point charge. So this single point charge that I have zoomed in will experience a magnetic force in accordance to the right-hand rules of forces. But also, since the negative charge reservoir is on the opposite side, since this one going up ni siya, which is going to the pool of positive charges, since again opposite charges attract, it will also experience an electrostatic force on the opposites towards the pool of negative charges. Now, this will continue. Wait lang, guys, ha. Sorry, before that, I forgot. So, di ba, may electromagnetic force, magnetic force, and electrostatic force exerting on the charge. Now, this separation of charges, since there is a separation of charges, that means, and there is an electric field, that means they will create a voltage. There will be a voltage, and that voltage is ang ginatawag nga induced voltage, which is in our Faraday's law of electromagnetic induction. Okay, now this induced voltage will only form when there is a balance between the the magnetic force and the electrostatic force exerted on the holes. Okay. Now we know. Now we know from it's from Coulomb's law of electromagnetic. We know from Coulomb's law that the magnetic force on the point charge is equal to Q times the velocity times the magnetic field strength. Okay. Now also electrostatic force. Rather, the electrostatic force by the Coulomb's law is also equal to the magnetic charge divided by times the electric field. Remember, the definition of electric field is the amount of force exerted per point charge. Okay? So that means, substituting these two expressions here, you will get Q VB is equals to QE. So these will cancel out each other out. Therefore, I'm running out of board again. Therefore, oops. Therefore, the electric field is equals to the velocity of the electric field on the within the conducting material, or the conducting wire, or the straight conducting wire, is equals to its velocity multiplied by the magnetic field strength that it experiences. And now, since we know in our previous lesson that the voltage is equals to the electric field strength, the electric field strength on the point, on the opposite, on the charges divided by the length, divided by the distance that separates between the charges. Now, assuming we go back here, assuming that these reservoirs are directly in line or collinear, or rather, what do you call this? Coplanar. The correct term is coplanar with this ends of the conducting rail, or in our native, in our mother tongue, tupong sila sa conducting rail. Therefore, the distance between them is equals to the width L of the conducting rail, which is this one. Which is this one. Substituting this expression to here, we get this. We get this one here. We get this expression here. And remember, since we have an electricity, since we have a voltage and it is connected to a conducting rail, wait lang. Therefore, the conductor on the conducting rail will actually form your closed circuit. Wait lang, erase ko lang ni guys. I'll be back. Okay, so let's draw our conducting rail again. We'll try to make it bigger. So, you have a conducting rail here. Wait lang, I'll adjust my camera para kakita ka mo. Oops. That's it, perfect. So we have a conducting rail here. And I don't want to use my blue whiteboard marker because it's a pain to remove it in this whiteboard. I don't know why. So here we have a conducting rail. We have our conductor here, right? And there is also a magnetic field here, XX, denoting that this is within the plane of the paper, or going in rather the plane of the paper. So it still moves at a velocity v, because once it stops moving, there will be the induced voltage will I don't know, it's incorrect term to disappear, but yeah, on a matter of speaking, the induced voltage will disappear because the charges, when it stops moving, that means there will be no magnetic force that moves the positive charges go up, or moves the holes up. Therefore, the holes and the electrons will recombine. What did I miss? Okay, so this is our conducting rail. Then we have Then going back here, we have a reservoir here of positive and negative charges. Okay, so since this reservoir is connected to wire, and this is the reason why there is actually a voltage, because this one acts like remember your battery, it has a positive and a negative terminal. So this reservoir of holes and electrons here is actually your positive terminal and your negative terminal in the language of electrochemical cells, or your batteries. Or in the language of electrochemistry, this is your anode and this is your cathode. Okay? Now, since the definition of electric current is a movement of positive charges, Wait, kitaon ang akong ring light. Flex ko lang akong ring light, guys. Look, if you can see at the right-hand corner of your whiteboard, the silhouette of the ring light is reflected there, and my God, it's so awesome. Joke. Okay, going back. So we have a positive and a negative terminal here. So since a current is a movement of positive charges, which as a chemist I personally rebuke, because I do not believe that that holes or vacant orbitals move. It's actually because vacant orbitals are not particles in physics they're considered elementary particles, which brings us to this endless debate of is a current a movement of positive charges or negative charges, etc. Anyway, so for the sake of physics, current is the current is a movement of positive charges, so it will move towards here, right? It will move towards here. So this motion is counterclockwise. It will move towards there. Now, since there is a current, so that means current, by Ohm's law, current is voltage over resistance, and that voltage is our induced voltage, right? So therefore, substituting this equation of the induced voltage to our formula, it is our current is equals to I VBL over R. So that's it. Now, if you want to get the power, the power produced by this induced voltage, so remember that the induced electrical power, or power in general, is equals to current multiplied by the voltage. And by Ohm's law, voltage is equals to current multiplied by resistance. So, therefore, the induced voltage is equals to I multiplied by IR, or I squared R, simply speaking. Now substitute the expression for the induced current in these in these symbols of in these values of current, it will yield to you. It will give you v squared, or sorry, VBL over R, quantity squared, times R. So distribute the exponents. So it's V squared, B squared, L squared over R squared times R. Cancel. And the induced power will be V squared, B squared, L squared over R. Okay? Now, since we're moving, let's go back here on our diagram. Ow, 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 ow. Now, since this one moves, since this circuit, since this conductor moves at a certain velocity with a current flowing through it, with an induced current flowing through it, now that means there must be some external force that makes you move the conducting rail towards this direction at a certain velocity. So let's say we're trying to pull the conductor to this direction. So let's say we have a force here that is F pull. Now, since, remember, there is a current going here, it moves at a certain velocity, and by the right-hand rules of fields, therefore, there should be a magnetic force in this going this direction, going to the opposite direction. Remember that we still have. Don't forget, you still have your external magnetic field, B sub O, which is going into the paper. So, by using the right-hand rules of fields, the magnetic force will go here. Okay. Now, in order for this to move at a constant velocity, by virtue of Newton's third law of motion, I'll erase this one again. By virtue of Newton's third law of motion, therefore, the magnetic force should be equal to the force due to the external pull. Remember that in order for it to move at a constant velocity, the net force should be 0, as indicated by the Newton's second law of motion, because Newton's second law of motion is equals to force is equals to mass times the acceleration, and since at constant v, or constant velocity, acceleration is equals to 0, therefore the net force should be equal to 0. That means in order for the net force for it to move at a constant velocity, that means these two forces should cancel out each other. So now, but since this is a mechanical, now we know that this is a mechanical force, and we have seen that at constant velocity, F is equals to 0. The force is equals to 0. So, paano nga may force pa na di Japon? Now, remember in our very first example earlier, that our conductor was pulled from its initial position W1 to the final position, wherein the distance between the width L of the conducting rail and the conductor wire is equals to W2. So that means there is distance. And remember that work is equals to force is it force times distance, right? And since my work, and since there is a time elapse, therefore, sorry. Sala ko, guys. I'm so sorry. Let's go back na lang sa this one. Magnetic field is equals to F pull. Now we know that in our lessons on magnetic forces, that the magnetic field, the magnetic force onto a current is equals to the current, is equals to the magnitude of the current multiplied by the magnetic field strength and multiplied by the length of the wire that carries the current. Since in our previous diagram, ang inimalanga move in this one, right? And the conducting wire is only in contact from here in this part lang. So the edges are actually there's no current there. So amo lang ning part ang may ang touch sa conducting wire. So that means the distance traveled by the current, or the length of the conducting wire, will be the width of our rail, which is ang L in our previous example. Therefore, magnetic force is equals to ILB, right? B null. Now, since current here, we have obtained that the induced current is velocity times this one over R. Therefore, we substitute this one here, so it will be like this one, and just distribute, so it will be B squared L squared over R. That's it. Okay? Now let's try some situations that there is what we have shown here is a change of the area perpendicular to the magnetic field strength. Amo na nga may induced current and induced voltage. So let's try some situations wherein there is a change in the magnetic field strength passing through your reference area or your effective area. And also, we'll try if there another example of a change in effective area. Okay. So let's have an example here. Let's have an example na I hope you can see. Yeah, perfect. That's it. Let's draw a ring here. Let's say this wire ring has a diameter of 6.2 centimeters. Okay, 6.2 centimeters, and there is a magnetic field here. Now, the initial magnetic field strength is equal to 1.65 Tesla. Now, after a time of 3.5 seconds, the magnetic field strength experienced by the metal ring decreased from 1.65 Tesla to 0.98 Tesla. Syempre, there is also an induced voltage. There will be an induced voltage, but by how much? So we use again the Faraday's law of electromagnetic induction, and now the delta t here will be our time t at 3.5 seconds. Now, since there is no change in the area, we did not move the ring or whatsoever, we did not decrease its effective area, therefore, our change in flux will be due to a change in our magnetic field. It will now look like this. Okay, I'm running out of whiteboard space again. So we get the area here. We get the area of the ring, which is the area of a circle. So it's pi r squared. We know that, and we just plug in our values for the area. Now from centimeters, I converted this to meters. Okay, right? Remember, guys, always before you plug in your values, always convert it to SI units. Okay. So 6.2 centimeters is equal to 0.062 meters. So the answer will be, I forgot the exponent here. So the answer will be 0.01208 square meters for significant figures. Now we have the area, we just plug in our values. So our induced voltage is now equal to 0.01208 meters multiplied by the difference in the magnetic field, the change in magnetic field strength, which is from 1.65 Tesla, it decreased to 0.98 Tesla. We will not concern about regarding the sign. There is a separate discussion for that. We will discuss that later on. Multiplied by the time, which is 3.5 seconds, and your final answer will be 2.312 times 10 to the negative 3 volts. Okay. So now let's say that, going back to the ring, let's say that the ring has a resistance of 0.03 ohms. So by Ohm's law, wait lang. Okay, I'll erase this one again. So by Ohm's law, current is equal to voltage, or induced voltage, over resistance, which is equals to 2.312 times 10 to negative 3 volts divided by 0.03 ohms, which is equals to 0.07708 ampere. Okay, that's it. So next we will discuss if another example of an induced current due to a change in the effective area of the magnetic flux. Okay, so let's have another example here, wherein we have a square or a rectangle made of a wire here, which has the dimensions of 3.4 cm by 2.1 centimeters, and a uniform magnetic field of 4.6 Tesla passes through it. It was shown that the magnetic field is perpendicular to it, and the rectangular wire, the rectangular shaped wire, is placed on a surface that is also perpendicular to it. Now, let's say this was tilted. Now, this was tilted towards the right, or the rectangle was tilted backwards after after let's say 4.0 seconds, it was tilted, like, so it will look like this. Whoops. I don't know how to show my, sorry. Wait. Whoops. So let's say amo na siya. Okay. So let's say amo ning surface. And we can show that it's tilted along the surface at an angle of 53 degrees. 53 degrees, okay? So now since the conducting rectangle has been tilted, that means this the magnetic field will no longer be perpendicular to the rectangular wire. So that means since there is no longer perpendicular to the rectangular wire, therefore the area the side perpendicular to it, this side perpendicular to it, is not equal. Let's say this is our W1 or W2. Now since this perpendicular side so this W2 is the one perpendicular to the magnetic field, therefore this will be the width or one side of the effective area of the magnetic flux that this rectangle is experiencing. So since there is already a change, there is already a change in the effective area, therefore there will be a change in magnetic flux after a time t. Therefore there is an induced voltage. Okay, wait lang. Whoops. Wait lang, guys. So now the induced magnetic field here, the induced voltage, or rather the induced the change in magnetic flux is equals to B delta A, okay? So delta A will be the difference between or the absolute value of the difference between the area after the area of the final magnetic flux and the area of the final initial effective area, rather, sorry. So given that the area is the area of the rectangular wire is multiplied by the length times the width, therefore the effective area, which is the area of the rectangular wire itself, because it is initially it is perpendicular to the magnetic field, so it will be 0.034 cm meters multiplied by 0.021 meters. So I did not show the conversion from meters to centimeters, that because it's pretty straightforward. So that will be equal to 7.14 times 10 to the negative 4 meters. Now we analyze for the area for the effective area after. So we know that it has already tilted. It has already tilted at 53-degree angle from this 53-degree angle away from the surface, which is also collinear or coplanar with the magnetic field strength, or with the magnetic field lines rather. So this is 2.1, and this is the one, the W2, this is the one that is perpendicular to the applied magnetic field. So we need to get this one. And based on our trigonometric functions, this is a right angle. If you can see, this part here consists of a right triangle, which means we can apply our trigonometric functions here. So if you can see, sine of the angle the angle which is the distance away from the surface is equals to opposite over hypotenuse 2 over 2.1, or we simply convert this to meters, 0.021. So W2 is equals to 0.021 sine 53 meters. So we substitute that instead of 0.021, we substitute the area, the width, to this value for area 2, or for the second area, into 0.034 multiplied by 0.021 sine 53. And this will give you an area of 5.702 times 10 to the 4th meter. So, as you can see, the effective area decreased once you tilt it. So, therefore, the magnitude of the induced voltage, we will not concern ourselves with the sign conventions for now. That will be discussed in the Lenz's law, is now equal to it's now equal to 0.03 wait lang. Our magnetic field, which is 4.6 Tesla, multiplied by the difference of the areas, which is 7.14 times 10 to negative 4 meters, minus 5.702 times 10 to the negative 4 meters, divided by time, which is 4.0 seconds. And that is equal to 1.654 times 10 to the negative 4 volts. So that's it, okay? So you will be encountering other problems that are far more complex than these. So what you just do is you need to not just look at electromagnetic induction at face value. So you really need to think really hard on how, or find another way on how to solve this rather peculiar problems, okay? So lastly, we will now discuss Lenz's law. So Lenz's law, it's not Lenz's. I will correct my previous pronunciation of Lenz's law. It's Lenz's, not Lenz's. It's Lenz's law, which is formulated by its namesake, which is Heinrich Friedrich Emil Lenz, coincidentally the same year that Faraday discovered electromagnetic induction on a separate study, which is in 1931. So he formulated this law in the direction of the direction of the induced current produced by a change in the magnetic flux. So now we know that when we move our bar magnet onto a coil here, there will be a reading. Okay, so if you notice in Faraday's experiments, the reading can go usually oscillates from the positive or the negative from the positive reading to a negative reading when you move the magnet up and down. Okay. Now, since there is a movement And since there is a change in magnetic flux, obviously, there will be a current going through here, okay? Now, however, what will be the direction of the current? That we do not know. So here in Lenz's law, it focuses not actually on the direction of the current, but rather the direction of the magnetic field that this induced current produces. Remember that I will reiterate this, that a current is a flow of charges. Now, since there is a movement of charges, that means there will be a creation of a magnetic field, and that induced magnetic field will oppose the change in the magnetic flux. Now, so example, since if we move our magnet towards the if we move the northern part of the magnet towards the wire loop, whose magnetic field lines are denoted by these arrows, so that means the current will also induce a magnetic field, will produce an induced magnetic field opposing to that motion nga pakadto sa imo nga current loop, okay? And by virtue of the right-hand rules of fields, since the induced magnetic field is going up, therefore the direction of the current will be going here. So this is our induced magnetic field, this one. So our current will move through here. So that will be, if we're facing this direction, so in this direction, that will be counterclockwise. Okay. Now, if we denote, since the downward motion is an increase, since the motion towards the coil increases the magnetic field strength felt by the effective area of the coil, that means the downward motion means an positive increase in the magnetic flux, a positive change or an increase in the magnetic flux. Consequently, the sign of the current will be positive, okay, and so consequently the induced voltage will also be positive. So now let's say if the motion will be downward, the motion will be away from the coil. So if the bar north south so since the motion is away from the coil, that means there will be a decrease in the magnetic flux felt by the coil there. Now, since this is in the opposite direction, going away, so the induced magnetic field of the current will be on the opposite direction here. Papanaog siya. So by the right-hand rules of forces, right-hand rules of fields, the current here will be going clockwise. Now, what is my basis that an increase in magnetic field is positive and magnetic flux is positive, and the decrease in magnetic flux is negative? So remember that magnetic flux is equals to a decrease in magnetic flux is the magnetic flux after and magnetic flux before the change. Okay, now since at this direction the final magnetic flux will be, if you're going away, the magnetic flux after the movement will be lower than the magnetic flux before the movement. And in this case, if it's going towards here, if it's going towards the coil, the magnetic flux felt by the coil after moving the magnet towards it will be will be greater than its magnetic field before, its magnetic flux before it was moved towards the coil. So, as a consequence, ma-positive yung mga induced voltage, ma-negative ang induced voltage. Similarly, your induced voltage here will now become, your induced voltage here will be negative, and at the same time, your induced current will be negative as well. Oops, it's not visible. Wait lang. Okay. So, this is the end of my discussion for electromagnetic induction. I will post more videos regarding on topics regarding electromagnetic induction. So, I think that's it. See you.